Good afternoon, everyone. First of all, I would like to thank the organizers for giving me the opportunity to talk about my work in front of you. Actually, this work I have done in my MSc fourth semester project, and the work is done in collaboration with Dr. Rakha Dasgupta, Assistant Professor, Department of Physics, University of Calcutta. So, here is the brief outline of my work. Here I will describe first that how bosonic double well can be compared with Josephson junction. And next, we will see how oscillating and self-trapping transition occurs there in the bosonic double well in terms of number difference between the two wells. Next, we will make some change in the double well system. We will make the tunneling between the wells non-reciprocal. And hence, we will see that our closed system will get converted to an open system. And finally, we will check how the non-Hermiticity of self-trapping affects our system. So, first of all, I will try to say something about Josephson junction in a brief. We all know that Josephson junction is nothing but a thin layer of insulator switch between two superconductors, which constitutes a weak link between the two. Is called a Josephson junction. Here you can see there are two superconductors in two sides, and in between there is an insulator. And we all know that in superconductors, Cooper pair carry the main role of conductivity. And when we are in a Josephson junction, you can see that Cooper pair can tunnel through this insulator even at zero external potential difference applied between the superconductors. Now, it is our double well system. Here you can consider one well as psi1 and another well as psi2, and our bosons will remain in this case either psi1 or psi2. Now here we will try to draw some similarity between the double well system and our previously spoken Josephson junction. You can compare that there are superconductors in both sides. Here is two quantum states in both sides. There are insulating layer in between. Here is potential barrier in between. Now, here is the description of the double well system. As I told previously that psi1 and psi2, there are two wells or two states, and boson can occupy these states psi1 or psi2. And we are considering the system such that the atoms in states psi1 or psi2 can interact with each other. We have considered the interaction constant as U, through which particles can interact with each other in any of the states. And there is also another thing, that is one particle can tunnel from one state to the another state, and also in the vice versa path, which was compared like the Josephson tunneling, and the strength of tunneling is taken as J. First of all, I will speak that the tunneling rate from psi1 to psi2 and psi2 to psi1 is taken same, means the tunneling strength is always J. Now we have tried to write the Hamiltonian for this system in terms of U, J, and annihilation creation operator. What is the annihilation and creator operator? AI dagger is the creation operator which create a particle in the state I, and AI is the annihilation or destroyer operator which destroys a particle in the state I. So if we expand this term by breaking the summation, we will get like this. Where the first term in the Hamiltonian represents the interaction between atoms, and the second term indicates the tunneling between the two wells. Next, we know if we have a Hamiltonian, we can use Heisenberg equation of motion to calculate the equation of motion for the system. So here we have calculated the equation of motion. Now here I want to say that we have replaced the operators by their expectation values. The reason behind this is that here we have considered too many particles. So in this case, we can take our operators like classical objects. Hence, we have replaced the operators by their expectation value. Now, we introduce a phase factor to solve this equation and get like this term, where Z is the particle number difference n1 minus n2 by n1 plus n2 between the two wells, and phi is the phase difference phi1 minus phi2 which is the phase difference of particles between the two wells, and nt is the total number of particles of the system. Here we can see that time derivative of z is non-zero, time derivative of phi is non-zero, but time derivative of nt is 0. It means the total number of particles in our system is conserved. That's why nt is not changing with time. So we can say that our system is a closed system. No particle can enter our system or no particle can exist from our system. Now, in this system, we have tried to see the variation of z. Z means the number difference between the particles with respect to time for different value of u. We can see that the z value is oscillating both sides of the z equal to 0 line up to a certain u critical limit. But when we cross the u critical limit, we get that the z value get trapped in one side of the z equal to 0 line. It means that our particles get trapped when we cross u greater than uc in one of the way. Now, this was our known system which we studied, and it is a physically observation, experimental observation. When u less than uc, you can see that the red color indicates particles. Both sides there are particles, but when u greater than uc, you can see that in one of the wells there are particles, but the another well is totally empty. Then this is our new work, whatever we have done. Actually, the previous Hamiltonian was Hermitian. We try to make in our new system the Hamiltonian as non-Hermitian. But how we do non-Hermitian? We make the tunneling strength non-reciprocal. It means previously we took the tunneling strength is J from psi1 to psi2 and psi2 to psi1. But here we consider if OL1 to OL2, the tunneling is J, OL2 to OL1, the tunneling strength is J plus J tilde. J tilde is like a perturbation like term. It can be positive, can be negative. So for this system, new system also we calculate the Hamiltonian, but here the change is that J1, J2 are not same. One is J plus J tilde. And in the similar way, we solve the equation of motion. Next, also by introducing a phase factor, we calculate the equation, we solve the equation of motions, and here get Z dot, phi dot, and nt dot. But the interesting thing is that previously we had non-zero Z dot, non-zero phi dot, but here we get a non-zero nt. It means in this case, the total number of particles of the system is not conserved. So particles can enter our system from external box, or particle can exist from our system. Next, we have tried to see the variation of Z, phi, and nt in our new system. Actually, here I have written when J tilde equal to 0. It means if we put J tilde equal to 0, it means tunneling reciprocal, not non-reciprocal. It is like the previous system. So we can see that here there is variation of Z, variation of phi, but nt is constant with time. It means when J tilde equal to 0, the total number of particles remains same, and it is nothing but our old closed system. But when we take Z tilde not equal to 0, there we can see Z phi t is time varying, along with nt is also time varying. It indicates by making system non-reciprocal, it means J tilde not equal to 0 gives our system to become an open system. So from an external box, we can particle can enter or exist our system. Now here also we try to see the variation of Z with respect to time. As the previous case, here also when we cross the critical limit, we get a self-trapped state. It means particle gets trapped in one of the wells. Now here we try to see the variation of UC. It means critical UC, after which the particles get trapped in one of the wells. How it varies with respect to J tilde. J tilde was the external perturbation which we added in the tunneling to make the tunneling non-reciprocal. We can see that with J tilde, UC varies almost linearly. When we increase J tilde, UC is also increasing. Now the main interesting thing is that when we put J tilde below a critical J tilde, then we get the number difference all time self-trap state. It means whatever be the value of U, we always getting Z as self-trap. But why so is occurring? It was an interesting thing to observe. Now we will try to explain this. So for that, we have to go back to our equation of motion for the new system. These are the equation of motion. If we compare this equation of motions with I h cut d psi dt equal to h psi, we can get by comparing the Hamiltonian matrix, which will be a 2 cross 2 matrix. Now we all know that how to find out the eigenvalues of this matrix and get eigenvalues like this. These are the energy eigenvalues for this Hamiltonian. Now, if we put J tilde equal to 0 here, you can see the eigenvalues will be like that. Now, please carefully look. If we put any value of u here or here, we are always getting a real eigenvalues. Lambda plus and lambda minus always is real. So, whenever J tilde equal to 0, we are getting from the Hamiltonian two real eigenenergy. It means when J tilde equal to 0, our Hamiltonian is Hermitian, because Hermitian matrix always gives us real eigenvalue. But look here, here we can get either lambda plus lambda minus real, or we can get complex depending on the value of J tilde. So we previously told that when there is J tilde, a perturbation term in the tunneling, we are making the Hamiltonian non-Hermitian. Here also you can verify it that our eigenvalues may be real, may be complex. It indicates that our Hamiltonian has become non-Hermitian by making J tilde equal to non-zero. So we can verify it. Now our main task is that how and where we are getting lambda real and where we are getting lambda complex by in terms of J tilde. Here we are plotting the real eigenvalues with respect to u by varying u for J tilde equal to -1. You can see there is a curve which is continuous curve. One is lambda plus, one is lambda minus. You can see this is continuous curve. It means that we are getting always real eigenvalue. But when we are going J tilde equal to -2.01, you can see here is some real eigenvalues, here is some real eigenvalues. Actually, it is a real plot, so you cannot show the imaginary eigenvalues. But look carefully, here is a discrete gap. It means there is some imaginary eigenvalue. So when J tilde is less than -2.01, we are looking that there is some exceptional point which differentiate between the real and imaginary eigenvalue. So here the interesting thing is that this J tilde equal to -2.01 is almost similar with this, where we got a totally self-tapped state. So from this we can conclude that non-reciprocal tunneling makes the system non-Hermitian. Non-Hermitian matrix may have both real and imaginary eigenvalues. There will be exceptional part that separates real and complex eigenvalues, and the concept of exceptional point indicates why below a critical J tilde we got totally self-tapped state. So here is a summary that non-reciprocal tunneling is making our system an open system. Self-tapped state. Thank you.
Right, so now I'll come to the judges for their questions.
What is the Cooper pair?
Cooper pair is actually it is a pairing of electrons that acts like a boson, and in superconductivity it takes the main, it acts as the main carrier of superconducting current.
Conductor, why Cooper pair carries the current?
Actually, in superconductivity, we have seen that below a critical temperature, we get normal conductivity to superconductivity, and to explain the superconductivity, we introduce the concept of Cooper pair, and by forming Cooper pair, the total, we can say that total resistivity of the system reduce, and hence the electron can flow.
Superconductivity is superly conduct. So
Yes, sir. Yes.
That is it. And one more thing, one more question.
Yes, sir.
Is that what is your Bose-Condensate? You started, the title is Bose-Condensate, but you never mentioned Bose-Condensate. You talked about that maximum had potential, and then talked about superconducting sandwich,
Yes, sir.
some non-conductor and all. But where is the Bose-Einstein condensate?
Actually, sir, here we are considering a double well, and here the particles are actually in the ground state by both condensation. They are after the condensation we have got this. Actually, the particles has remained in their ground state by condensation.
So post-condensate, that's what that should be the conclusion.
No, sir. Actually, here the particles are in their condensed state. They are bosons. They are in their ground state, and their tunneling. We are comparing that their tunneling is like the Josephson tunneling.
Alright, but how do you relate this picture to your next slide picture, where you can use one insulator by two superconductors on both sides?
Yes, sir. Actually, sir, here are two superconductors and an insulator in between. We know that when there is a AC Josephson junction, we get that Cooper pair can tunnel from one superconductor to another superconductor, and there occurs a certain phase difference between them. Yes, sir. Here also we have shown that when particles from this side to this side goes, we have shown that this phi, what is the phi 1 minus phi 2, this also is varying with time.
I guess my question is exactly related to this.
Yes, sir.
Yeah, so I can be loud. So what we understand from your presentation is that you have a Josephson junction where you have two superconductors and an insulator is sandwiched between two superconductors.
Yes, yes.
And to model that system, you are using the double well potential, where the insulator is like the barrier and the two superconducting states are what are the ground states?
Actually, ma'am, that is not like that. Actually, we are studying this system. This system first we have studied, but to introduce this system and its tunneling, we have seen that there occurs a phase difference, phase change.
Yeah, if we get to the question,
Yes,
so then the question comes is that if your presentation is about looking at a double well potential and the asymmetric tunneling strength between these two minima,
yes, ma'am.
Yeah, and what effects it has, etc., etc. So the problems that you solve, that's just studying a double well potential and asymmetric tunneling.
Yes, ma'am.
So that, but then you started your presentation with a Josephson junction. So my understanding was that you are trying to model the Josephson junction using a double well potential, and we're going to learn something about conductivity in a Josephson junction with your model. But that is not.
No, not.
Okay, thank you. That was just an example.
Yes, ma'am. Yes, ma'am.
Are there any other questions from the audience? So, do you have any questions?
Thank you for the talk. What I'm understanding is the double well potential is equivalent to the superconductor.
No, superconducting tunneling is equivalent here with the tunneling between the two double wells particles.
So my question was that in the illustration of superconductor, could you show that?
Please.
So illustration of the superconductor that is shown in the next slide, could you show that? Yeah. In this case, it is being illustrated that on both the sides, it's acting kind of like a free particle, and in between it's like a potential barrier, right?
Actually, in superconductor there is no free particle. In superconductor there remains Cooper pair, which takes parts in the superconducting current. So in both sides, if there is no insulator, the superconducting Cooper pair can go through here to here. But
his point is that the way you view the picture, there it seems like in both sides is just plain wave. So that's the free particle, and then there is tunneling in between.
Yes, ma'am. Yes,
we do a classical
yes,
tunneling.
That is like quantum mechanical tunneling, and here the amplitude is more, but when it tunnels from one side to another side, we know in the tunneling the amplitude gets reduced.
My first question is that basically the potential that we choose, the Wechsler potential, it was, if you only consider one side, has a kind of parabolic nature. So that won't have a free particle wave function. So how do we make that equivalent?
I cannot understand.
I think the answer is that this is just a pictorial.
This is nothing. You do not connect with this.
Are there any other questions? There are no questions.
Thank you. Thank you.
Thank you, ma'am. Thank you.